Our speaker today is Marco Leona, the David H. Koch Scientist in charge of the Department of Scientific Research here at the Metropolitan Museum of Art. He received his undergraduate degree from the university in Pavia, Italy, and his PhD in crystallography and mineralogy at the same university in 1995. He completed a fellowship at the Conservation Research Laboratory of the Los Angeles County Museum of Art. Then he joined the Freer Gallery of Art at the Smithsonian Institution in Washington, D.C., where he conducted research on the techniques and materials of Japanese painting. After a second period at Los Angeles County Museum of Art as senior conservation scientist, he moved to New York to head the newly created Department of Scientific Research here at the Met. As a scientist working in an art museum, Dr. Leona enhances art historical and art conservation research through the application of scientific techniques. The scientific examination of works of art allow identification of their constituent materials and manufacturing techniques, dating and authentication, the investigation of aging and degradation mechanisms, and the monitoring of environmental conditions in display and storage areas in the museum. His own interests are in the elucidation of material aspects of art production, either for the enhancement of our knowledge of past cultures or the preservation of their material vestiges. Please join me in welcoming Dr. Marco Leona.
Thank you. I apologize for the delay. Please accept my apologies. I'm very glad you're here, and I'm very glad you invited me to speak to you. I'll try to give you an overview of what the department does. Hopefully it's going to be different and new with respect to what you may have seen before in this same place. I have to say there have been a lot of things that we've added to our repertoire and to our interests, and I hope that this will resonate with you. Can everybody hear me? No. Can everybody hear me now? Very good. I know that this room sometimes has problems. Normally I'm mic'd here and I'm flapping my arms around the stage. Has everybody seen this slide before? Excellent. Why do I start with it? Because I like to say that what Hercules is doing there is a little bit like what we are doing. I don't think we have a boring day ever here at the museum. Our problems look a little bit like the problem Hercules is dealing with, in the sense that as soon as you think you've grabbed the problem by the head, it turns and bites you somewhere else. Likely we have tools, and they are a little bit better than, let's see. Oh, no, come back. They are a little bit better than what they aren't better. They are a little bit better than a club. We also wear better garb. You won't see us running around in lab coats. We were recommended not to do that at some point by somebody very high above. And I'll leave it at that. But anyway, so really I think there's truly an element of improvisation and creativity in a good sense. The job is never standard. We don't have routine, really. That's bad for a scientist because routine helps you improve what you do. In a sense, it's like CSI or forensic science, except that what you see in TV is not a good representation of what the real forensic work is, because they do everything really by the book and by routine. We have to improvise much more, so we look more like the TV people. We're not as good looking, though. But this is a good example also of our work, because it's a real piece of art. It's a Limoges plaquette, so it's a piece of copper with glass powders and metal oxides that are fused on top to create the image that you see. When the curator brought it to us, she was slightly befuddled by the signature and the date. That would have been a very early signature for, I think, Fernand Limousin, because his father was still alive at that time. So for the son to sign the piece with his name at that date would have been slightly unconscionable. And so we analyzed it to detect whether it was a forgery or an authentic piece. And by examining the composition of glass materials, you can, by finding out certain marker elements, determine the age in which when it was made, not by some numerical technique, let's say such as carbon-14 that tells you exactly an age, but by comparing two pieces of known provenance and age and seeing if the recipe is the one that was used at that time. And we see that there's a very good correlation between recipes, time, and area of provenance. So this piece, instead of being found to be a 16th century French piece, was found to be French, but 19th century, which is an interesting result in itself. It's a time in which there was interest in the medieval period, in which there were reproductions and forgeries of art. So in a sense, we find an older, collectible perhaps, quite nice, forgery or imitation. And that's definitely one thing that we do a lot here at the museum. We really work on these three lines. We're concerned with the materials aspects of works of art. What's in a work of art, how it got there, how the work of art was put together. So in a sense, I like to say we look for the human hand behind the work of art. We're not much into the aesthetic and inspirational and creative aspects unless they really touch to the material aspect. So that's why I'm saying we try to complement, hopefully enhance, what our colleagues in art history and conservation do. A big driving force behind our work is, of course, the fact that the museum is very active on the market. So we acquire a lot of art, and having a laboratory that in-house can vet your acquisitions, if you want, on a third degree from the stylistical, iconographic, provenance exam that we can have from the curatorial side, some technical exams that we can have from conservation, you have scientific analysis on top of that. So a lot of really vetting and authentication of pieces. We can also, as we did with the plaquette I just saw, refine an attribution or help determine a provenance, again, by steering with the materials clues the attribution more on one side or the other. When pieces are undoubtedly what they're supposed to be, we can then analyze them just for the pleasure of finding things out with a modicum of course, concern for the art. We don't like to do things just because, but imagine that now you have a collection of Van Gogh drawings that are perfectly provenance. We can examine them in a very microscopically invasive or non-destructive way to see how Van Gogh was working. You know that he was writing a lot about his choice of materials, and so we can compare what's in the piece to the written evidence. That also tells us something about the evolution of the piece, whether a piece, the way we look at it now, is exactly how we intended it to be, whether we need to worry about something or try just to keep it the way it is. In this piece, we were working with the curator of works of art on paper to look at Van Gogh's choice of inks and dyes. It's the time when modern synthetic dyes come on the market and artists start experimenting with it. So what you see in the fez of the Zouave is a combination of historical pigment, if you want, the classical pigment used by all artists up to Van Gogh, and new synthetic dyes. And some of the appearance may in fact be due to the properties of these new materials. There's another component which is properly called conservation research, and it's the work that we do to support new conservation treatments, to understand degradation of works of art, and to try to remediate it, either in an active way to help the conservators develop new approaches, new interventions, but also in a way called preventive conservation, making sure that the museum environment is of such a quality that preservation of the works is assured. That means measuring pollutants in the air. That means working with the facilities in the building to ensure that air conditioning is set at the proper values for the best outcome. You know that wood can split and break when it's too dry. You know that it can become moldy when it's too wet. We want to be in between. Sometimes the conditions that are best for wood are not good for metal. You could have corrosion in relatively high humidity. So that's all part of our purse, if you want. We've been doing a lot more on that. And then we do something that I'm more involved with personally, just because I like that, which is developing new techniques for our analytical work. As I mentioned, that we have to be very careful when we analyze objects, not to damage them. A lot of chemistry is fairly invasive. Traditionally, you want to take a big piece from the object you're analyzing to make sure that your results are accurate and representative. Clearly, we cannot do it here. So we work with the most microscopic samples. We're literally talking about something that could be thinner than a hair. And in some cases, we develop techniques that are what we say non-invasive, so that the work of art is not touched. You'll see some examples. The museum, you probably know, is a very large place. It's the largest footprint for any building in New York. You know, you may think of Empire State Building as bigger because it's taller, but nothing has the footprint that we have. And just imagine of the complication that carries for the art, for moving the art, for preserving it. I'm sure that you've walked most of that extension in your life at the museum. But some of the numbers are staggering. The ones I'm more concerned with are the number of objects, the number of loans, the number of curators, and the number of conservators. Those are our customers. So we have, 215 customers, 2 million patients, and there's 10 of us. Positively scary. More so the fact that this could be one of our patients one day. This is from the Psyche Young exhibition on the roof, but I could show you the Damien Hirst piece or a number of them. This also gives you an idea of the situation. We're a museum in a big city, in a park, with 4.5 million people coming in and out. So, it's easy to talk about conservation when everything is isolated and quiet, but we are such a production here that there really are many things to keep into account. We have a lot of techniques helping us, and I'm going to give you a little quick overview. As I say, some of them are commercially available, some of them are customized from what's commercially available, some of them are put together here. Here you see two of my staff. We'll meet them later also, on the screen. They're working on gas-chromatography mass spectrometry. This is a technique very used in pharmaceutical analysis, in toxicology, clinical analysis. It's what they use to see if athletes take some kind of doping. What it does is that we can take a very small sample from a painting and use it to identify the binder of the painting, let's say linseed oil versus walnut oil, or mixtures of oils with proteins, resins, and whatever an artist may have used to create a paint that suit his or her purposes. As you can see, that can be both used for attribution or could be used to pinpoint some conservation problems that may be more typical of one artist versus the other. I used to say, this is exactly like an instrument you could see on CSI on TV. I'm not saying that you watch CSI. I know you're watching PBS and Masterpiece Theater and all that. But with a big difference. In CSI, they put the sample in, which is injected where they're doing that thing there. And 5 minutes later, they say, we have a match. And I swear, the instrument looks like that, like mine, but we must not have paid enough. We got a lemon, because it takes us days or a week to get something. So remember, if you ever watch TV. Anyway, we use, that's the wrong title. This is not what you see in the title. We use microscopes to examine our samples, again, because they're very small, but also because we want to see details inside the samples that are very fine. Think about the way an artist builds a painting. There are many layers. The ground, maybe a priming, a paint layer, glazes, varnishes. We want to be able to go on to all those layers and identify them, to track the progression and to see maybe what's restoration, what's original, and how each artist worked. And we can do that with that thing there, which is an infrared microscope that can see layers as thin as 10 micron. Now, a human hair, if you have a, let's say a child or a blonde person with thin hair, it's about 50 micron. That's 50,000th of a millimeter. And a millimeter is about 1/24th of an inch. So we're talking about something really thin. And we can do that with the microscope, which has become a really great tool. We have been working with electron microscopes for a long time now. The advantage is that you can see a high-resolution, high-magnification image of a detail of an object, get an elemental analysis. So, for instance, if you're looking at jewelry, you will know the title of the alloy. You will know exactly how much gold, silver, and what other alloying elements that may indicate forgery or use of recycled metal or whatnot. In some cases, and with the instrument that we have now, we can actually put the whole object inside without any damage to it and look at it, look at the detail on this object. I don't have the picture here, and that's too bad. We work with a specialist in the history of jewelry, and he was looking at some of our Roman jewelry, those pieces with the very detailed filigree, and they are amazing to see at the electron microscope because you can see what the technologists of 2,000 years were able to do, and it's just unbelievable. That's a way also to see if, instead of being Roman, it's 19th century, because the methods of working gold change, and we can see some of the tool marks. We've been pioneers in the US with a new technique called RAMAN microscopy. You will hear a lot about microscopies and spectroscopies, and I apologize if I sound repetitive. On the other hand, I apologize if I assume that you don't know the difference, but I get a lot of that with my colleagues here. Of course, they're all different techniques, different spectroscopies. We look at all kinds of different phenomena, and different microscopies. When I say microscopy, it's because we put a microscope attached to the instrument to work with our small samples. Here with Raman, we take a laser beam, send it to the sample, and from what comes out of the sample in response to this laser beam excitation, we get a fingerprint of the object. We can do it like this on a microscope setup, but also you'll see later, we do it on, we can actually turn the microscope around and do it on the art directly, and that's a non-invasive way. This machine here, liquid chromatography, analyzes dyes that are found in objects such as tapestries and textiles, and again, it's a great study, it's a great tool to trace exactly the origin of those pieces. That's what I said about the Raman. We can use a probe, so a fiber optic tool that can actually go against a work of art, in this case a 19th century lithographic poster, and bring the signal back to the spectrometer. What we're using it here for is to analyze the dyes contained in the inks used for the poster. By studying them ahead of time, before any conservation treatment, we know what they are. We can go back to the books and read the properties so that we can advise on the best course of action for treatments. Let's say they want to wash this poster to remove soiling from the surface. It's important to know that there are no water-soluble inks. And some of these dyes used at the turn of the century, the previous one, where water soluble. So we want to avoid bleeding, and by knowing, we can do that. Of course, you could do it with a small test, but in this way, it's completely non-destructive and safe for the work of art. We developed some of this RAMAN instrumentation, which is a big passion of ours, in-house also. This is a different instrument where the microscope has been blown up so that we can actually put really big objects underneath the microscope, not just a microscope slide. And here one of our student interns is working on Greek statuette. So it goes under there, the microscope, and we can look at the surface in high magnification and find pigments and other materials. We're trying to come up with techniques also completely from scratch. The previous one was an instrument that we slightly modified. Here we're trying to use fluorescence spectroscopy. We're working on the reverse of the Burgos tapestry. Those of you who are familiar with textile conservation may have seen this very large Spanish Renaissance tapestry being conserved. This is the reverse, of course. You see all the loose threads. And we'll see if by shining a light through a fiber optics on the fibers and collecting the fluorescent light that comes off, we can identify the dyes. And here I'm working with a colleague from Florence, and he developed a mathematical system to process the data. It was very promising when we used it on our reference samples, all the little dyes and textiles that we had here that are all clean and nice. But when we went to the real works of art, it unfortunately fell apart, which is another thing to remember. Works of art are extremely complicated. You're looking at very high-end productions, very complex recipes. You're looking at the effects of time, 500, 600 years of aging that may have changed how things look, so that when we build our techniques and we calibrate them on modern materials or things that are made now, even using the old recipes, we always have an element of disconnect. You know, we have history behind and time between us and the art. So it's very difficult to reproduce exactly what's happening. So our methods have to be so much better. So we're still working, trying to improve this approach. A newer techniques that we're really applying for the first time in art is here at the Met, is nuclear magnetic resonance. And you know of that from MRI and from the medical uses. It can have very valuable, it can give very valuable information for art conservation. It's done here not with the hospital type setup, but with a much smaller tool, which is the kind of box that one of our students there is putting against this test panel. Just imagine it's that big magnet has been squeezed into something as big as this. It won't give you the kind of information that you get from a medical MRI, but it's sensitive to how the materials underneath the box are, let's say, rigid or soft. And it has a certain ability to track, to probe in depth an object. So we can use it to see what is the state of conservation, for instance, of a painting. It can tell us whether the oil layer has degraded to a certain extent or is it still pristine. It can sense that kind of shift. And we think it's very promising because the only way to get that kind of information is to remove a sample and look at it in sections. So this would be fairly nice. You know, if you're talking about MRI, it's the difference between an MRI and a biopsy. So we think there's something to gain there. Of course, this type of research requires us to go to universities, try to entice our colleagues in academia to work with us, requires going out to foundations and science funding agencies and trying to get funds to support them, because when you deal with universities, nothing is free. I'm sure some of you are dealing with tuition, you know that. But anyway, what are some of the actual projects that we have going on? What I found interesting and challenging. We've been working for a while with the analysis of Greek and Roman statues. In fact, we have some messages on the audio guide, and we have the podcast, and we have some of these new web things like YouTube and iTunes. And here it's an interesting example. You may have seen in the Greek and Roman courtyard these two imperial statues of youths of the imperial family. They're like twin statues. They're on the east side, sort of in the middle, just before you get to the Bosco Reale cubiculum. They're remarkable because the drapery has a trace of purple pigment. And of course, we think, well, it could be the imperial purple made from shellfish. You sort of see it there. So if you can trace with your eyes where that fold goes, you may be able to see that there's a faint, it looks brown here, but it's really purple. You can go to the pieces and you will see it. Just imagine it's somewhat here. So if I were wearing a toga today, I could show you. It's sort of here. Colleagues tell me that it's not exactly a toga, but you know, that's what it is. This piece is actually fabulous because if you looked at it with a microscope, unfortunately we don't have a microscope in the galleries, you would see that it has little specks of gold. So it actually also had gold leaf to simulate gold thread. So it was the richest type of embroidery. There's so little remaining in these piece that we cannot take samples out to identify these purple dye and to tell you it's really imperial purple or it's a substitute. And so we're still trying to develop a technique that will give us that answer. No technique currently available can do that. You could say, why do you need to know? And you may have a point there. I set myself up for this. But I think there is some interest. First of all, you know, the answer that people would say is because it's there. Well, we've heard that. But to me, it's actually interesting to know, is this really the purple dye that would cost its weight in gold and that was used only for the textiles for the emperor and the senators and so on, and which is really a terrible material to paint on marble? It makes no sense to use it. Or is it another pigment that would be cheap that you could put on and then repaint when it's necessary? These things were out in the sun. That tells me something about the way people in the Greek and Roman world were working and were thinking. And so I think that's why it's important to go in and do scientific studies on the pieces you have. It really adds more to the collection and to the way we look at these pieces. We're using all kind of new techniques when we can. As I say, I wish we had an instrument like this to look at the purple. We can't. This is a portable X-ray fluorescence analyzer, an instrument that will look at metals and other elements present in a sample. Here I'm looking at a Mycen, cute dog. It looks quite nice. I wish they had it at the store. It looks positively evil. The colors turn out really well. It's orange. And this instrument allows you to go to the object, test what's in there. Unfortunately, it works only for elemental analysis. You know, if you want to know iron, chromium, gold, it doesn't work for molecular analysis. If you want to know about the dyes, linseed oil, organic things. But again, that's why we have a complementary approach. We have instruments of all kind and people with different specialties. Again, another example here, I'm working on the setting up an alternative technique for that statue. Here you see it sitting down, and here that's, again, that purple stripe. This time we're trying fiber optic reflectance spectroscopy. Essentially, we're measuring the color and seeing if it looks like any dye we know. Unfortunately, it didn't look like any dye we know. Perhaps there will be another possibility for that type of approach with a new technique that we developed here that I worked on and for which we actually got a couple of patents. And I think it's a promising avenue of research. Here we're trying to use a very sensitive approach based on the, if you want, the frontier of nanotechnology. We take these dyes, these organic molecules, we extract them, and we couple them with metal nanoparticles. And that thing seems to sort of like amplify whatever property they have. So amplify their response to external stimuli. So if you send a laser beam to a particle that has been treated like this with a nanoparticle, you get a much brighter response, if you want. And maybe that will help us here. And what I'm doing here is I'm using a little gel, a polymer gel, which is clipped onto a thread. We tested it so far on textiles. And the polymer gel is clipped onto, put in contact with a thread, but it could be on the surface. And very slowly, very gently, it will remove a little bit of the dye from the textile without requiring us to cut the thread, without actually fading or bleaching the dye, because such a microscopic amount is removed. And then we analyze the gel instead of the textile, and that has proved very, very, very interesting. We're trying to expand the use to things like analysis of documents, analysis of ink on paper. A lot of other. This, of course, is not the only problem that we have. We're covering 5,000 years of history and 5 continents, all kinds of materials. So besides, we're hopping back and forth from organic, inorganic, metal, glass, whatnot. This is the type of work that we do in relation to the problem I showed at the beginning, the analysis of the enamels, a lot of trace analysis of glass. We do a lot of electron microscopy and micro analysis of glass so that we can pinpoint all of the elements that are found at any given time and all the trace elements. So what we're building here is a database of glass compositions. Here you see a lamp, possibly used in a mosque, so but clearly an Islamic piece. A lot of these pieces were made in imitation of Islamic pieces in the 19th century. So having the possibility to know whether something is 13th century Syrian or 12th century Persian versus 19th century French is quite important. Some of these pieces, the 19th century French, were not made as forgeries, but their history may have been lost and they turn up on the market as the original thing, which is clearly not something you'd want to buy unless you were looking for French glass. Deterioration studies, so properly the conservation research type work, take us in all kind of direction and all kind of collaborations. Here we've been working with the George Eastman House in Rochester, which you know has a great collection of photographs. We will work also with the Boston Museum of Fine Art for a study on daguerreotypes. And here some of my staff are investigating the deterioration processes that affect daguerreotypes. Here you have a really high magnification photograph of a daguerreotype. And if you are sort of careful, you can see, if you sort of like make up what's here, you can see a beginning of a dimple and the edge of a lip, and all of these spots that should not be there. They should be uniformly dark, or should be dark with whatever shading there's there. And this is unfortunately Miss Lola Montes, the way she looks now. Something happened in between. Unfortunately, I have to say, when the daguerreotype was under our care. I mean the museum, not myself. I wouldn't have been able to do anything. I was not here in '98. But something happened, and it's related to, actually, it probably happened while it was on loan, but something happened in between here, I swear. Something happened in between here where the silver surface of the daguerreotype was really affected by some factor. And what we were able to do, we were able to go in there and detect chlorides, which are typical corrosion products that you may find on silver, and we think are related to some storage or exhibition condition that either exposure to material that are not appropriate or a climate change that led to this kind of deterioration. These are, you know, on a daguerreotype, essentially almost irreversible phenomena. So what we want to know is that we can at least stop the progression and make sure that everything else is stored in such condition that will not cause further damage. But the science that you need to go in here and really find out what these are and therefore what was the problem is not trivial. It's not as simple as putting it into the electron microscope and detecting the corrosion project. Likewise, I'm sorry if I'm bringing always cases of bad cosmetic conditions, and ladies, that may say something. But paint also is not immutable. Oil painting, some of the most stable works of art, if you just judge from what we have, from what period, are actually, in a sense, living objects. They evolve. They follow the rules of physics and chemistry. Well, you see it, first of all, in the craquelure. So these surfaces are not immobile. But things happen under the surface as well. This is, of course, who is it? Too easy. This is, of course, Madame X, and what we could see happening to Madame X was that some areas of, I think, the black, so the hair and the background, were actually showing these phenomenon where little tiny spots, white spots, were appearing. And we had to go in and remove very small fragments. We did it from the background, not from the hair, so that we could see in depth what was happening. And we found a phenomenon. So what happens is something like this. Just imagine that the canvas, which is not, would be here. This has been removed from the canvas. This is about 2 millimeters long, so it's not too big. The canvas would be here. This is the paint layer, the top. And these are all the various components from the ground up. But what you see is this white material that forms and pools and sort of wants to go out like a volcano. It looks a little bit like a commercial for things to remove zits and stuff like that, which is essentially what it is. But what you have here is that this paint contains lead white, very common lead paint, essentially. It also contains linseed oil, and what we and colleagues discovered and found to happen very often in old master paintings and generally in traditional oil paintings is that some of the fatty acids that are contained in the linseed oil react with the lead pigments, dissolve them to a certain extent, form some other crystals, these white things here that are called lead soaps, and they can pool. They will create pressure as they try to grow, and they want to go towards the surface because of humidity gradients or other things like that. And when they come up, they break through, or the surface can be easily abraded, and they show as white. This was first found on Rembrandt paintings in the Netherlands, so it's by no means something that it's happening only here and bad Metropolitan Museum scientists. It's something that we need to study more. It's really a big active research at all kinds of museums. Now, the fact that we have to take these samples to see that it's happening and to characterize the extent is why we're interested in techniques like MRI or NMR, as we do it here. Because if we can do it straight from the surface of the painting rather than taking this piece off, of course, it's all the better for everybody, and the conservators and curators are much happier with us. So that's the direction of research we're moving on. I mentioned the environment many times. You probably realize moving from gallery to galleries that suddenly you're feeling draft, you're feeling colder or hotter, things change. This is a very complex building to balance. We have storage, office, galleries. We have essentially, physically, at least 7 buildings. Somebody would say that we have as many buildings as we have curatorial departments. But it's a very, and the buildings grew with time, right? We've had the William Morrison, the McKee Mead and White, and then Sackler Wing, and then everything, and we put glass covers over courtyards. It's an extremely complex environment. We're in a big city with the traffic, with the sea, so we may have chlorine coming from the sea. We have nitrogen oxide and sulfur oxides coming from the traffic, coming from heating. We have all kinds of dusts. We have the visitors. They bring in a lot of dust, fiber from clothing and all that. We have the park, so we may get all kinds of animals and pollens and dust. So that's why we did, a few years ago, the first air quality sampling at the museum. Here you see some colleagues who actually came from Belgium, from a group that specializes in environmental studies for cultural heritage institutions. And we're on the roof over the Asian wing. You've probably never been there. It's fabulous. And we're in August. It's great to do this in August because we had to set up some strange-looking equipment here looking at Fifth Avenue. And I really wanted to avoid strange phone calls to the director from the neighbors. We addressed that by putting a relatively innocuous-looking thing towards Fifth Avenue, and we put the really scary one towards the park. So, you know, nobody called us from whatever, the San Remo or the Majestic, I don't know. What are we doing there is actually sucking in air from outside, and then it will be analyzed with a variety of chemical techniques to look at sulfur oxide, nitrogen oxide, particulates, ozone, all kinds of pollutants that we know can affect the art. And we do the same inside, in the galleries, and in the cases so that we can have a real clear picture. We will have to do this every 5 years maybe to see how things evolve, and of course it has a cost, and it's very difficult to explain that that is part of our mission. We do less complex testing on the cases. So whenever you go in a gallery and you see cases, we actually have tested all of those materials to make sure that they don't, as we say, off-gas any pollutants of their own. Think about it. You open a cabinet, you can smell the paint, you can smell the wood. Old furniture, you can smell sort of like an acetic acid vinegar smell sometimes. And that's just wood, it's natural, but it's really bad for art. So that's how we try to control that and avoid that. There's another part of the environment, which, as I say, sometimes our visitors bring in, sometimes just comes in by itself from the park. Sometimes it comes hitchhiking on other works of art, and it's insects. You can't get rid of insects anywhere. And they live in space even, apparently. And we try to control that. We do something called integrated pest management, which means that you try to keep good hygiene and conditions so that you don't have insect infestation. But when you find insect infestation, and sometimes, as I say, things come from outside, hitching a ride on a crate or on a piece of art, you have to do disinfestation. We can't call the guys with the big pump and spraying around because, of course, that's not made to work on art. So we use a technique that we perfected here called argon anoxia. And anoxia means absence of oxygen. Argon means that you put argon in place. And argon is a very inert gas. It's entirely safe for the art. but it doesn't support any type of respiration process at any biological level, meaning that it will kill molds, it will kill fungi, it will kill insects. And the way we do it, we make these bags. Here you see our record. I think it's a 10-meter long bag, which we set up in the Textile Conservation Lab, where we had to disinfest a storeroom of textiles. So they're all in here. This is 10-meter, which is, 30 feet. And we have off camera an argon reservoir that's pumping argon through and displacing oxygen so that in 5 weeks, all the little bugs will be dead and the art will be well preserved. That's, you would be surprised, but it's actually a big requirement because of the big acquisition and loan schedule. One of the, again, I say conservation research is about developing new techniques. When I joke with my fellow scientists, it's about developing simple things and giving them a complicated name. And I think we have our ACE treatment here. You will remember probably what the facade looked like before we cleaned it 4 or 5 years ago. It looked like this. Here I have the comparison of what it looks like now. I mean, this is in between phases. The facade is limestone, which means calcium carbonate, and the black crust is really a product of the traffic and acid rain and pollution on reacting with that calcium carbonate. It forms gypsum, which is calcium sulfate, and it traps soot particles from heating, fumes from the cars, so that's why it looks black. Now, one of our scientists worked on that a lot. He's a specialist on architectural preservation, and what he found was that, which is known from basic chemistry, calcium sulfate is slightly soluble and certainly slightly more soluble than calcium carbonate. So we thought, well, all we need to do is wash these grime away. Of course, it's not straightforward because we didn't want to scrub. We didn't want to use any pressure washing, which is what is used normally in residential and commercial buildings. We wanted to find a very gentle cleaning method. You could say, well, why is rain not cleaning the facade? Because even now rain is slightly acidic because of pollution, so it actually keeps the phenomenon happening. It's rain in the first place that does it. Very simplified. So we came up with this system called water mist cleaning, and which is implemented like this with about 100 or so very expensive equipment. So if somebody needs a lawn sprinkler right now, let me know. These were going on hours on end, but what they provide is very gentle cleaning, and the results are there for everybody to see. And again, this is something that with just essentially a little bit of chemical knowledge, but a lot of common sense we could implement here at the museum. Where are we going? I think I gave you an outline of what we do, and essentially we're going along those same lines, trying to improve and make everything better. We really are bringing in all the technology that we can because our customers and our patients demand that. We can't do that by ourselves. We need to work with academic labs, and we're working with the City University, City College, with NYU, with Princeton, and with labs farther away to get our academic chemistry colleges colleagues interested in the area of research that we're doing and integrating our efforts. And then we've invested a lot, and we'll keep do that, in areas that were previously not served very well. The study of organic materials, so you've seen some examples on paintings, but think about modern art, think about modern design and furniture, the use of plastics, synthetic resins, and their conservation problems. and more on this topic of the museum environment and what I call, and many call, preventive conservation, making sure that the environment in itself is a conservation tool rather than a deterioration tool. And I think that's all I have for today, but I'll take all the questions you may have.